It's always wonderful to be back in Oxford. It is scary how quickly people change. But it's lovely to be seeing new faces. So, let me launch straight into the talk, and I'll give a quick caveat. The paper this is based on is, in various points, reasonably technical and reasonably long. I, at least, don't take in detailed mathematical results that well in verbal form, so I tend not to expect others to either. So I'm going to kind of present a somewhat broad shape of the thesis and skim over various of the technical details. And I'm happy to explore aspects of that insofar as I can in the discussion period afterwards. So, thermodynamics, counterintuitively, is not a theory of dynamics. Dynamical theories in physics are concerned with what systems spontaneously do. Their characteristic form is something like, here is the space of possible states of the system. Given that the system is currently in this state, here is the state it's going to spontaneously end up in 5 minutes from now. Here, perhaps, is the state it was in 5 minutes ago before it spontaneously reached this stage. The paradigm of dynamics is the closed system. Notwithstanding issues of the quantum measurement problem, the paradigm involvement for the observer and the agent in dynamics is to get out of the way and just watch. Dynamical theories are about systems left to themselves behaviour. Thermodynamics is not like that. What does thermodynamics say about what systems do if left to themselves? It basically says systems evolve to equilibrium and stay there. So by definition, systems at equilibrium don't stop being at equilibrium. Equilibrium is by definition the state that systems settle down into. So what thermodynamics is concerned with, instead, is the kind of transitions that can be brought about in a system, not by their own spontaneous behaviour, but by the intervention of an external agent. Thermodynamics is concerned with what happens when you push or prod or stir systems, place them in thermal contact with other systems, shape them around, and do all sorts of other things to them. There's a general term for that kind of theory in science. Theories of this kind are called control theories. I should just come across, I don't mind. Control theory is concerned with what kind of transformations you can bring about in physical systems by externally intervening on them. In thermodynamics in particular, we're normally concerned with a rather specific control problem, that is, problem of what kind of transitions you could bring about. We're normally interested in the question of how much energy, sometimes other conserved quantities, but usually energy, how much energy can you get out of the system by some certain class of operations? So, for instance, I might have some collection of warm systems or some collection of pistons and cylinders of gas and this kind of stuff. And I might be saying, okay, that's all very well, it's all very pretty, but I need to charge my phone. And so I want to see how much energy can I get out of this so that I can shove it into my phone battery. Okay, so a couple of answers to that question. Naive answer the first. You can't get any of a conserved quantity out of a system. What did you think conserved meant? Conserved means quantity does not change over time. If you get it out, it changed over time. What that misses, of course, is that from a broader perspective, quantities are only conserved within closed systems, and if you're intervening in the system is no longer closed. What we can say is to say the system on which we're intervening plus the intervener themselves, well, maybe that's a closed system. And so, precisely because energy is conserved, then the decrease in energy of the system being intervened upon is going to equal the increase in energy of the intervening system, of the intervening agent on the system. So then we realise, okay, just because the quantity is conserved, that's not at all a bar in getting some of it out. So that suggests the second naive answer. Get all of it out. What constraints could there be? I mean, maybe there are practical limitations, but beyond the conservation, what restrictions could there possibly be on one's ability to get energy out of the system? And of course, phenomenological thermodynamics, by which I mean the thermodynamics that was developed empirically, largely in ignorance of the micro-world in the 19th century, gives an intermediate answer here. It says you can get more than none of the energy out, but less than all of the energy out. And specifically, the amount of energy you can get out is constrained by the second law of thermodynamics, as well as by energy conservation. And I'll say more about how I'm understanding the second law in a moment, but you can basically think of it here as a constraint that says not all transformations that conserve energy are possible even in principle. If, in fact, all I have is a single system of fixed size and uniform temperature, I can't get any energy out at all. It doesn't matter how hot it is. If it's isolated from other systems, other than perhaps me, then, and all I can do is modify its parameters, then I can't get the energy out. If I have two systems, like a hot one and a cold one, and I'm allowed to put a heat pump between them, now I can get some of the energy out, but not all. And when eventually the hot system cools down and the cold system heats up, and maybe at the same temperature, now that's the end of the game, I can no longer get any energy. So you can think about phenomenological thermodynamics as a control theory characterized by a controlled problem, the extraction of energy from a system, the ability for the system to do work on the intervening agent, if you like, and by the first law, conservation of energy, and the second law as constraints that tell us what the space of control operations are. And now, if we look from a modern perspective and remember that we want to understand the microphysics of thermodynamics and not simply the phenomenology, there are two attitudes one finds to thermodynamics, and specifically to the second law of thermodynamics, in the literature. Sometimes I should say simultaneously from the same person, but in any case, different corners of the literature. The first attitude is the second law is something about big systems. It's emergent, it's approximate. It holds as a consequence of something like large number statistics and the crudeness of our interventions. Anytime you're told in a stat met course something like, well, we use thermodynamic methods because we don't have the ability to track everything about the system, then you're seeing this kind of idea. And this is tied to the idea that thermodynamics itself, not just the second law, is itself an emergent and approximate system. A classic way thermodynamics is used as an example in philosophy of physics is as a supposed paradigm of emergence, of reduction, of a higher level theory that holds approximately when, for whatever reason, the full lower level theory is too complicated or misses the wood for the trees. And again, in this tradition, then the second law is only going to hold statistically in the first place. It's only going to be like, on average, you can't decrease entropy. On average, you can only get this amount of energy out. And for a sufficiently clever agent, a light-fingered demon, to use the classic example, who can manipulate systems on the microscopic scale and keep track of every last molecule, then even the statistical form of the second law might be violated. So here's a quote from Maxwell illustrating this idea of the second law. The second law of thermodynamics, says Maxwell, has the same degree of truth as the statement that if you throw a tumbler full of water into the sea, you cannot get that same tumbler full of water out again. You cannot, in the sense that the odds are massively against you, but it might happen just by fluke. And if you're super careful about keeping track of every water molecule, maybe you can finagle it into happening reliably. That's take one on the second law. Take two on the second law counts this as something more exalted, something exact, something universal. It casts the second law of thermodynamics as a fundamental constraint on physics, something that constrains us no matter what. Applicable to large systems and small. You see much discussion in various bits of the statistical mechanics literature of things like the thermodynamics of a gas containing a single molecule. You see extraordinary experimental work these days testing the second law and testing other bits of thermodynamics involving individual stretched strings of DNA. And on this tradition, it's impossible even in principle to violate the second law. So if on the first tradition, Maxwell's demon characterizes the fact that you can violate the second law if you're clever enough, on this second tradition, the various attempts to get rid of the demon in 20th century physics, to exercise the demon, to borrow John Ehrman and John Norton's term for it, gets at the idea that it shouldn't be possible to cheat your way around the second law, not even statistically, not even approximately, not even if you're very clever indeed. So there's a couple of quotes here that it's actually obligatory as a kind of guild requirement to put in any talk about thermodynamics, so I'll put this in here. The first of those is Einstein's famous quote, that thermodynamics is the only theory of universal content concerning which I am convinced that, hedge, within the framework of applicability of its basic concepts, it will never be overthrown. I'm never quite sure if Einstein's kind of hedging there incidentally. I mean, there's a certain sense in which I want to say, Newtonian mechanics within the framework of applicability of its basic concepts will never be overthrown. I mean, almost by definition that's true. Anyway, there's a more exalted reading of Einstein there that's getting at the idea of thermodynamics as something that we just don't ever find a way around. Perhaps even better known is Eddington's quote. People mostly probably familiar with this. I gave a lecture to this to a specialist audience on philosophy of statistical mechanics, and I just put Eddington quote on the slide. Because not everyone here is a specialist in statistical mechanics. I'll give it to you to read out. The law that entropy always increases holds, I think, the supreme position among the laws of nature. Someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, paraphrase, you're screwed. So what I want to do in this talk is to look at how one reconciles these two senses of thermodynamics. That is, how one reconciles the idea that thermodynamics, and in particular the irreversibility of thermodynamics that's characterized by aspects of the second law, seems to be very tied to coarse-graining, large-scale structures, things that apply because of the limitations of our interventions, with this more exalted notion of thermodynamics, this idea that the second law is some kind of principal constraint. And to kind of spoil the end of the talk, what I'm going to argue and develop is that irreversibility is genuinely connected to emergence, approximation, to some extent to macroscopicness, but that even in the complete absence of irreversibility, there are principal constraints on our control theory set by the second law that transcend simply or exceed simply the requirement of the conservation of energy. And again, I should say that as with more or less any piece of exploring the foundations of a theory as old as thermodynamics, trying to say something new is often more about organising and bringing ideas in a particular way than bringing something that no one's ever thought of in any form at all. So for any given comment I make, don't necessarily take it as an original observation, far less a brilliant one. And I'll refer people to the paper this is based on for a rather more sort of detailed analysis of how this connects to various parts of the extant literature. Okay, so what I want to do with that preamble set is start by saying a bit about in a bit more detail, what phenomenological thermodynamics looks like, just to remind ourselves what the structure is of the thing we all learn as undergraduates, and perhaps show a bit about some of the features of that aren't always stressed in the foundational discussions. And then I want to go on and talk about how we think about the microphysical groundings of that, and start to see how assumptions about irreversibility and macroscopicness and the coarse-graining of our interventions start to plug into the framework. So, lightning course in phenomenological thermodynamics. We start with systems. A system in thermodynamics spontaneously achieves a state of equilibrium. Harvey Brown here coined this the minus first law of thermodynamics. Thermodynamics doesn't say anything really about non-equilibrium other than the fact it's undesirable, systems stop being at it. Thermodynamics in quantitative form is all involved in characterizing the equilibrium states. And specifically, the equilibrium states are characterized by three things. By the total energy of the system, but also by some collection of external parameters and some collection perhaps of other conserved quantities. So the paradigmatic example of the external parameter is how big is the box the system is in. And the paradigmatic example of another conserved quantity is how much stuff is in the box. And the idea of equilibrium is that, finessing certain concerns about spontaneous symmetry breaking, the equilibrium states are individuated entirely by the conserved quantities, including the energy, and these external parameters. I think in Harvey's way of putting the minus first law, something like any isolated system confined in a space of fixed size spontaneously achieves a unique state of equilibrium. I think we can helpfully generalize that outside some of the classic thermodynamic examples. Any system constrained by certain external parameters, such as size, achieves a state of equilibrium characterized only by the value of its energy and other conserved quantities. I take it that's a friendly amendment that's very much in the spirit of your minus first law, Harvey. So if systems aren't if a system isn't at equilibrium, well, it's still characterized by that external parameter. It's still characterized by those conserved quantities. The conserved quantities aren't changing because they're conserved and the system is isolated. So the system spontaneously goes to the equilibrium state. And so you can know, prior to it equilibrating, what equilibrium state it's going to reach, if only you know the conserved quantities and those external parameters. So, for instance, a rock. Rock shape is fixed. We're not going to heat it up enough to change its shape. A rock, as a thermodynamic system, is characterized by its energy and nothing else. A system containing a fixed quantity of gas, 5 moles of hydrogen, say, is characterized by its energy and by the volume of the box. To some extent, you can see here that what we regard as a system is a little bit optional, a little bit discretionary, because I could also regard that same system as containing a variable quantity of gas that just so happens to be 5 moles of hydrogen in the here and now. Now the system is characterized by its energy, its volume, and by a conserved quantity, the number of particles. If the box contains black body radiation, it's characterized by its energy, it's characterized by its volume. It's not characterized by the number of photons in the box. Why not? Because photon number is not a conserved quantity. A system with a certain number of photons in can spontaneously evolve to a system with a different number of photons in. The only conserved quantity is the energy, and the external parameter is again the size of the box. A ferromagnet sitting in the external magnetic field, the energy is the only conserved quantity that matters, and the field strength is now an external parameter, playing a similar role in the thermodynamics of the ferromagnet as the volume of the box of gas plays in the thermodynamics of the gas. And I didn't put it on to avoid hostages to fortune, but between ourselves, black holes will do fine as well. Black hole is characterized by its conserved energy, by no external parameters at all, and by its conserved angular momentum and its conserved charge. All right. Here's the control theory of phenomenological thermodynamics in a nutshell. It's constrained by the first law. The energy required to carry out a transition equals the change in energy that's induced by the transition. That's almost definitional, but of course the definition rests on the fact that we know energy is conserved not just for that system, but it continues to be conserved as a broader metric when you couple to another system, as long as you consider that system's energy as well. And here's the second law in a highly non-operationalized form. That's the kind of form one actually ends up with at the end of one's Foundations of Thermodynamics text. For any given thermodynamic system, there is a state function, an equation of state, which defines a certain function, the thermodynamic entropy, which is a function of all those parameters. In other words, if you like, it's a function on the space of equilibrium states, but because the equilibrium states are characterized by energy, conserved quantities, parameters, then the state function is a function of energy, conserved quantities, parameters. And any transition inducible between otherwise isolated systems has to be non-decreasing with respect to that function. Again, hopefully this is just revision, but just to get to sort of settle on some terminology and ideas. There's kind of also a third principle that's not exactly a law but tends to come into play here in practice, which is something like, and that's it. In other words, provided you conform to the constraint of the first law, provided you can conform to the constraint of the second law, you can basically do anything else you like. You can if there's a transition that's entropy non-decreasing, and you pay the energy budget and maybe the other conserved quantities budgets, and you adjust the external parameters if necessary, you can bring that about. Or maybe you can get as close as you like to bring it about. Maybe I can't actually perform any transformations that don't increase the entropy, but if I'm slow and careful about it, I can keep it down as low as I like. I'm not going to put that as a formal rule, but it's often there as a tacit extra constraint. All right, that's phenomenological thermodynamics. If that's all you have virtually nothing, because almost all the actual content of phenomenological thermodynamics applied to any particular system involves working out what that state function actually is. It's only if you know what that state function actually is for a given system that you can start saying specific things about how much energy you could get out by what kind of particular manipulations. And as long as thermodynamics is a phenomenological subject, then the only real way you can get that out is to ask the world. There are tabulations of the state function of water at the back of thermodynamics textbooks from the 19th century all the way to more or less the advent of Google and Wikipedia. And for many systems, we can't actually do any better today than just to empirically measure the equation of state. But for many other systems, we think we know how to calculate it. And there is a recipe for calculating it. And the foundational status of that recipe is deeply and darkly contested. And the most important thing I want you to take away from this bit of the talk is, notwithstanding all those deep and dark contests, the damn thing works. In other words, the recipe for calculating from microphysics what the equation of state is, which I'm going to call the canonical recipe, there's an enormously deep and important question to which we'll return as to why it works. There is no serious question at all that it works. Here's the recipe. Again, I hope this is largely revision for many of people. So at the microscopic level, and by the way, for this talk, I'm going to talk classically, just for simplicity. Nothing I'm saying here really depends on classical versus quantum mechanics, and in fact, if you want to do the formal version of this, it's actually a bit cleaner in quantum mechanics, because the math of quantum mechanics is often a bit simpler for these kind of things. But for these purposes here, and to avoid getting ensnared in the quantum measurement problem, I'm going to use classical mechanics as my go-to case. So, classical mechanical system. My thermodynamic system is represented by a phase space. It's represented by a family of Hamiltonians on that phase space. A family because the Hamiltonians are parametrized by the external constraints. So, for instance, if my system is particles in a box, then my Hamiltonian includes a kind of schematic presentation of the walls of the box. It might have a kinetic energy term, plus some little interparticle interaction term, plus an external potential that's flat inside the box and goes very steeply to infinity as you approach the edge of the box. And if I have other conserved quantities, likewise I represent them by functions on the phase space, perhaps parametrized by the external parameters. And then we define this familiar thing, the canonical distribution, for any given values of the energy and the conserved quantities and the external parameters. Then the canonical distribution is this sort of familiar Boltzmann thing. There's a missing minus sign, sorry. E to the minus h minus mu n over t. If you don't remember how to do chemical potentials, pretend there's no conserved quantity, and you'll see the even more familiar rho of u comma v equals e to the minus h of v over t. If you're puzzled by the v, just got to take it as tacit for any given volume. That figures a Hamiltonian. The canonical distribution for that Hamiltonian is e to the minus h over t, up to a normalization factor. And then, what are the parameters in this? What is this t? What is this mu? In the canonical recipe, definitionally, they're those values such that the expected value of the Hamiltonian with respect to it gets you back to the original energy you started with, that the expected value of any other conserved quantities gets you back to the conserved quantity values you started with. Why did I define this thing? Well, because once I define it, I can calculate the state function directly. The state function is just the Gibbs entropy of the canonical distribution. What's the Gibbs entropy? It's for any distribution minus the integral of rho log rho of that distribution. Why has that got anything to do with thermodynamic entropy? Watch this space. Does it have anything to do with thermodynamic entropy? Well, if you use it and you calculate the state function and you check that against the experiment, you get the answer right. And if you did it to a system that no one's done yet, they'll give you a Nobel Prize for it. Okay. So that's our starting point. That's thermodynamics as we confront it in practice. That's phenomenological thermodynamics and what we in fact do to give it a microphysical underpinning. And I think, by the way, this is a general comment on the philosophy of statistical mechanics and the philosophy of thermodynamics. I think a problem a lot of this literature tends to have is that it doesn't spend long enough reminding ourselves what the quantitative thing is that the theory gets before it starts discussing the foundations of why and where it gets it. And you'll sometimes get discussions, for instance, that will discuss how we should define the entropy in microphysical terms, and it will justify, say, for instance, you follow the Boltzmann's idea, and you think that entropy is somehow associated to the size of a volume of a region in phase space, and then you ask, why do we want to take the logarithm of that region in phase space rather than just take the volume of that region to represent entropy? And you'll hear various stories about, well, it's because it's convenient for entropy to be additive, or this has nice mathematical properties that make it more useful to us. No. The entropy has the value it has because it's an empirically measurable quantity in thermodynamics, and if your theory does not return the correct numerical value of that empirically measured quantity, you haven't fulfilled your responsibility. So let's try fulfilling our responsibilities. Let's ask why that canonical recipe should get the answers right. And let's start by clearing our throats. The first worry one has, and this has worried many people in philosophy of statistical mechanics, is the very fact that we wrote down probability distributions when we started doing foundations of statistical mechanics was something to get really worried about. Why were we imagining we could characterize a physical system by a probability distribution? How can those probability distributions, which one naturally thinks get connected to our own ignorance of what the system's like, how can they have anything to do with these objective, I've been stressing empirical, thermodynamic properties? There's a particularly vivid quote of this by David Albert. Can anyone seriously think that our merely being ignorant of the exact micro-conditions of thermodynamics plays some part in bringing it about, in making it the case that, say, milk mixes into coffee? Albert says dissolved, milk's not soluble, but his point is not substantially hurt by that correction. However, quick comments to reassure you on this point. So firstly, it's true that there are puzzling things that happen in statistical mechanics if we understand the probabilities of statistical mechanics epistemically. If the probabilities of statistical mechanics reflect my ignorance of the actual state of a system. But it's worth remembering that epistemic reading of probabilities is optional. It's contested just how we should read probabilities in any context, but for instance, statistical mechanical context. But don't jump automatically from I'm characterising the system probabilistically to those probabilities must in turn be characterised epistemically. Maybe they should, maybe they shouldn't, but that's an additional piece of reasoning. Second observation, and this links to the first, this isn't actually optional in quantum mechanics. Here's one of the places I will allude to quantum mechanics in this talk. In classical mechanics, you can reasonably draw a clean distinction between the probabilistic state of a system, some distribution in a phase space, and the microstate of a system, some point in phase space. You can't do that in quantum mechanics. If you ask what's the classical limit of even a quantum mechanical pure state, it tends to be something like a probability distribution over the phase space. If you ask if I've got some large quantum system that breaks into subsystems, and even if that large quantum system is in a pure state, generically the subsystem will be a mixed state. Whereas in a classical situation, if I've got some large composite system and the whole system is represented by a given phase space point, and then the states of each subsystem will be represented by phase space points. So long story short, the mathematical equivalents of the probability distributions are just non-optional in quantum mechanics. And this just in quantum mechanics is true and classical mechanics is false. So classical mechanics should only really be of interest to us here insofar as we're saying things about it that carry over to the quantum case. Third and perhaps most emollient observation, Albert's criticism, whatever its virtues, in the study of non-equilibrium statistical mechanics, in the study of what things spontaneously do if left to themselves, doesn't really have bite. It doesn't really have bite in a control theory, which I've been saying is what thermodynamics is. If I say, how could it possibly be that my ignorance of that system can play a part in the way that system spontaneously evolves? That's a pretty concerning criticism. If I say, how could it possibly be that my ignorance of the system can play a part in what I can do to that system? Well, that doesn't have bite. There's no inherent problem with the idea that my ability to manipulate a system might depend relevantly on my epistemic access to that same system. So I'm happy to come back to that in the question. For the moment, I'll take as read that we're okay to carry on using probability distributions in a foundational context here. And to go back to my earlier point also, we better have some justification of doing so, even if it's only kind of pragmatic, because that's actually what works empirically when we try to calculate quantities in thermodynamics. Okay, so with that sort of starting exercise carried out, let's look in a bit more detail as to how we might justify the canonical recipe. And I'm going to suggest a justification that doesn't work because it's too naive, or probably too naive, and then I'll suggest a variation of it that looks like it might work. And here's the starting observation common between the naive and non-naive versions. There's a couple of chairs the other side of the room. I don't at all mind people moving across while I'm talking. So here's the observation that's a starting point here. If the control operations I carry out on a system are ultimately dependent on the laws of physics, then at least a large class of the operations I'm going to be able to carry out, at least those operations that don't involve entangling my own microstate with the system, are going to involve applying some kind of external potential to the system, causing the system to evolve under some dynamics that isn't necessarily Hamiltonian dynamics under the system's own Hamiltonian, but is Hamiltonian dynamics under some Hamiltonian or other. Or if this was quantum mechanics, is unitary dynamics under some quantum Hamiltonian or other. And the Hamiltonian control operations, if you like more formal versions of this, the symplectomorphisms of phase space, these transformations preserve this quantity Gibbs entropy that we saw earlier. We haven't said anything about how to interpret Gibbs entropy. It's a purely mathematical feature of probability distribution, but it so happens it's a mathematical feature of a probability distribution that is preserved under Hamiltonian flow. So here's a proposal. Our control, which I'm not really going to justify in much more detail here, it's reasonable to assume that our control operations are indeed Hamiltonian. And furthermore, it's reasonable to assume in phenomenological thermodynamics at least, that the time scales on which my control operations act are slow compared to the time scales under which the system spontaneously equilibrates. So for instance, the go-to example of a control operation on an isolated system in thermodynamics is I've got a box of dilute gas, it's got a piston, and I push the piston in. So the gas has a time scale on which, if the gas is not close to equilibrium, it gets close to equilibrium. And my pushing the piston in has a time scale. And claim, which you can pretty easily substantiate in that particular example, the first of those time scales is really short compared to the second phase. In other words, it takes me maybe 10 seconds to push the piston in. It takes, of the order of microseconds for the system to equilibrate, at least on short scales. So now, here's the naive idea. Suppose we think that equilibration is progression towards the canonical distribution. So suppose we think that when I take a system that's isolated and I allow it to equilibrate, at the end of the equilibration process, it's really in the canonical distribution. And that's a very natural thing to think, isn't it? That you calculate the features of the system by using the canonical distribution to describe it. How could that possibly get the answer right? Well, a really obvious thought is because it really and truly is in the canonical distribution, because that's the correct, actual description of the system, leaving aside some of the probability concerns from earlier. So if it was true that the process of equilibrium caused a probability distribution of any kind to spontaneously evolve into the appropriate canonical distribution, then we have a pretty good justification of the canonical recipe. And the justification would look like this. It would be control operations preserve Gibbs entropy, and as I carry out the control operation, the system is continuing to equilibrate, and equilibration, I should say, increases Gibbs entropy because the canonical distribution is, as it happens, the maximum Gibbs entropy state for given values of the parameters. So equilibration is increasing Gibbs entropy. The direct consequence of the control operation is preserving Gibbs entropy, so of course Gibbs entropy is non-decreasing, and whenever the system reaches equilibrium, its thermodynamic entropy is its Gibbs entropy. So any set of transitions that start and stop at equilibrium are transitions where the thermodynamic entropy is non-decreasing, and now we've got the second law. Okay, that can't be true, or rather, that can't be true as long as we've got the microphysics right. Because, we've said it already, Hamiltonian control operations preserve Gibbs entropy, and the word control is doing exactly zero work in that sentence. Insofar as equilibration is more Hamiltonian flow, Insofar as isolated systems equilibrate, and insofar as that equilibration doesn't violate what we normally think the laws of microphysics are, then Gibbs entropy is a constant of the motion. This is a classic problem in the foundation of statistical mechanics. So it can't go up. But here's a more plausible idea. Suppose equilibration, and this is, again, a standard idea in statistical mechanics, suppose equilibration is progression not to a distribution indistinguishable from the canonical distribution. Sorry, it's not, giving away my punchline, it's on the slide. Equilibration isn't progression towards the canonical distribution, but it's progression towards something you can't tell apart from the canonical distribution by the methods of your control theory. Well, if that was true, the way the system would behave, as I tried to control it, would be just the same as it would behave if it really and truly was spontaneously going to thermal equilibrium in the canonical distribution. And so anything I derive for what the system will do and what control operations I can carry out on the assumption that it really is equilibrating by approaching the canonical distribution will continue to be true if I assume it's approaching a distribution that I can't tell apart from the canonical distribution by any of the transformations I make. Okay, it's helpful to be a little more formal here, and it's also going to help us to generalize a little bit. So let me introduce the idea of what I call a coarse-graining map. I'll call, I mean, not, it was being so called by Zwanzig and people 30 years before I was born, so I won't take credit for it. But what following those people I will call a coarse-graining map is a map from distributions to distributions that has these properties. Well, firstly, it is a map from distributions to distributions. Secondly, it squares to itself. In other words, it's a projection map. You coarse-grain, and now you've got a coarse-grained distribution. If you coarse-grain the coarse-grained distribution, well, it's already coarse-grained. That was a waste of time. Nothing further happens. So J squared is J. Thirdly, it leaves the energy invariant. In other words, the coarse-grained distribution has the same expected energy as the uncoarse-grained distribution. I haven't mentioned and should have mentioned if there are other conserved quantities, it leaves them invariant as well. And the coarse-graining is entropy non-decreasing. The entropy of J rho, Gibbs entropy of J rho is at least as high as the Gibbs entropy of rho, and you only get equality when the state's already coarse-grained. I'll give you a bunch of examples of coarse-grainings in just a moment. Once you've got the notion of a coarse-graining available, you can start using it to describe classes of control theory that are characterized by the coarse-graining operation. And I want to be very clear before we go on. They're not characterized by the fact that I'm actually going to apply the coarse-graining transformation as a physical transformation. Coarse-graining transformation is entropy increasing generically, and so it can't be carried out by any Hamiltonian process. So when I say I'm going to use these coarse-grainings to characterize control theories, I don't mean I'm going to characterize them by saying the coarse-graining is actually carried out. Here's what I am going to mean. I'm going to say a class of control operations, curly U, forward commutes with the control operation if up to some very large number of operations that's finite but very big. It doesn't matter if I alternately evolve and coarse-grain, evolve and coarse-grain, evolve and coarse-grain, evolve and coarse-grain, or if I just coarse-grain, evolve and coarse-grain. So the idea is something like, from the point of view of my control operations, the details that the coarse-graining operation washes out don't matter, at least insofar as we check with respect to those same coarse-grained details later on. So, if all I care about at the end of the process is the coarse-grained details of the system, the details that are invariant under the coarse-graining, I can work out what those details are, either by just performing the coarse-graining right at the end of the evolution, or by alternating control operation, coarse-grain, control operation, coarse-grain. And again, the idea here is something like, my control operations aren't sensitive to those details. So what happens to the features of the system is going to be this, what happens to the coarse-grained features of the system is only going to depend on the earlier coarse-grained features of the system. That's the general framework I want to play with here. Yeah, sure.
So you think there are just two levels of the system, fine-grained and coarse-grained, so that's why J squared equals J.
Yeah. I mean, of course, you could perfectly well introduce a hierarchy of coarse-graining operations such that, J2 is coarser than J1 and write a framework of this kind, but I'm just doing it at one level here. And I also need to say, given J and given U here, a state row is forward compatible with this if the evolution of that state or the coarse-grained feature of that state likewise isn't affected by whether I start with the state, evolve it in coarse-grain at the end, or start with the state, evolve a little coarse-grain, evolve a little coarse-grain, evolve a little coarse-grain. And the way I want to characterize a theory using a control... I'll come back to that. The way I want to characterize a theory using a control operation is I want to say, look, my theory's characterized by some j if all the states the system could start in are forward compatible with j and with the control operations, and if my control operations are all forward commute with j. And you can also define a notion of completeness with respect to j, which is to say those are the only constraints. If I've got a transformation that does obey those rules, then I've got access to that transformation. I'm usually going to tacitly assume something like that, but it doesn't need to be formal. And a key feature of this is that, suppose I define a quantity I call the coarse-grained entropy. So the coarse-grained entropy of a state row is the Gibbs entropy you get if you start with row, coarse-grain it, and then calculate the Gibbs entropy. So that's a functional of any distribution. You give me a distribution, I return its coarse-grained entropy. It's not only a function of coarse-grained distributions, but its value on any given distribution is equal to the Gibbs entropy of the coarse-graining of that distribution. And you can see, hopefully fairly immediately from this, it's a couple of lines to prove formally, that if I'm acting on a system with control operations that are forward compatible with j, then those transformations leave the j entropy, the coarse-grained entropy, none decreasing. None decreasing, but generally increasing, notice. The Gibbs entropy is a constant of the motion. The coarse-grained Gibbs entropy is not. There's no bar to the coarse-grained Gibbs entropy increasing under dynamics. And this is crucial. There's no bar to the coarse-grained entropy increasing under Hamiltonian dynamics. It's not just that if you genuinely evolve the system by periodically coarse-graining it, then its coarse-grained entropy would go up. Yes, it would, but its Gibbs entropy would go up. It's that even for an evolution that's Hamiltonian, that leaves the Gibbs entropy invariant, there's no bar on the coarse-grained entropy going up. All right, that's the abstract framework. And let's loop back now to what we were saying about the equilibrium phenomenological theory, because that's going to be our first example of a theory characterized by coarse-grained control framework. So define equilibrium thermodynamics as the control theory I get if the coarse-graining maps any distribution at a given energy in conserved quantities to the canonical distribution. So this is characterizing the idea that the coarse-graining says the only features of the system I can control are those parameters which characterize this equilibrium. I can control it. I can control the external parameters. I can pull the piston out of the box or turn up the magnetic field. I can control the conserved quantities by pumping in more hydrogen gas or trying to get some energy out. But that's the only handles I have on the system. I can't get at the system more finely than that. So claim that kind of control theory is characterized by saying it's forward compatible with equilibrium coarse-graining, with throwing the system into the canonical state. Partial equilibrium thermodynamics says, okay, let's suppose I've got a bit more control on this. Let's suppose the system is broken down into subsystems. And each subsystem, at least as far as I isolate it from the other systems, has its own external parameters, its own energy, its own value of the other conserved quantities. And now I have the ability to isolate the systems one from another, to allow conserved quantities to flow from one to another, to make individual ones bigger or smaller. But I don't have any more control than that. So now the appropriate coarse-graining doesn't throw the whole system to equilibrium. It doesn't say, well, that's one big system with one big energy and one big number of particles. What's its equilibrium? It says, let's throw it separately to equilibrium in each step. So the coarse-graining now is partial equilibrium coarse-graining. It's taking the distribution to the product of the subsystem equilibrium distributions. Boltzmannian thermodynamics is finer grained than that and assumes more control than that. So, who's familiar with the idea of macrostates in Boltzmannian thermodynamics? Kind of about a third of people. So there's a classic idea. I'll just describe it briefly in Boltzmann's approach to thermodynamics that says break phase space of a big system into cells, into macrostates, which is characterized loosely as any two microstates in a given macrostate look about the same. There are sharper ways of doing it. And a given macrostate might, for instance, correspond to all the air in this room being smoothly spaced out at a certain temperature, or it might correspond to the temperature being warmer in this half of the room, or the pressure being higher in this half of the room, this half of the room. It might correspond to all the air in this room being in that corner, but it won't be more fine-grained than that. So any of the various ways all the particles in the room could be in that corner and have a certain overall temperature, those are in the same macrostate. And Boltzmannian thermodynamics says you can manipulate a system at the level of those macrostates, but no finer than that. So if I'm allowed to carry out a manipulation which depends whether all the particles are in the corner or whether they're spread out, but it can't depend on the fine-grained details of how they're in the corner. I don't have that level of control. So the appropriate coarse-graining there is a sort of smoothing out with respect to that partition into macrostates. We take the probability distribution and we make it uniform over each macrostate, but we still allow it to be very ununiform from one macrostate to another. That gives you Boltzmannian thermodynamics. And then we have reversible thermodynamics where there's no coarse-graining at all. So in reversible thermodynamics, the coarse-graining operation supposedly is the identity. We can do any Hamiltonian transformation we like in reversible thermodynamics. Okay, so let me say something about how to parameterize the amount of energy we can get out on these various coarse-grained theories. So notice, remember, that's the name of the game here. We're interested in the control problem of how much energy we can get out of a system by a certain class of control operations. We've now found a way of characterizing control operations by what coarse-graining operations they're forward compatible with. And so now we want to say, can we say something in terms of the coarse-graining operation alone that helps us work out what the upper limits are on that amount of energy we can get out? Okay, if I said no, this would now be a boring and anticlimactic way to end the talk. Fortunately, the answer is yes. Here's a way of doing it. So remember, for given parameters, the canonical distribution maximizes Gibbs entropy for those parameters. And under reasonable assumptions, which roughly speaking are the assumptions that mean no negative temperatures in thermodynamics, then you can turn that round and you can say the canonical distribution gives you the maximum Gibbs entropy for given energy and other parameters. So conversely, it gives you the minimum energy for given entropy and other parameters. Now I can, again, under reasonable assumptions, I can invert it. So instead of asking what in the canonical distribution is the entropy for given energy, I can ask what's the energy for given entropy. And just as the canonical distribution maximizes entropy for given energy, so it minimizes energy for given entropy. There are a few caveats there, but it's basically right. So here's the best move I could make. Given that my control operations are all non-decreasing in the coarse-grained entropy, if I've got a control process compatible with J, it's non-decreasing in the J entropy. So given that the canonical distribution is the minimum entropy state, and given I can't do any transformation that decreases J entropy, and given that the coarse-graining will leave the canonical distribution alone, so the J entropy and the Gibbs entropy are the same for it, my best option is to steer the system into the canonical distribution, reversibly, to try to transform my current state with whatever Gibbs entropy it has, so whatever J entropy it has, into the canonical state with that given J entropy. Because my state has some energy, I want to get some of that energy out, so I want to steer it into a lower energy state. Which state shall I steer it into? Well, as low an energy state as possible. So what's the lowest energy state I could steer it into? Well, I can't steer it just into the ground state, because the ground state has a lower J entropy. The best I can do is steer it into that state which has the lowest energy for given J entropy. And that's the canonical state. Or more accurately, it's some state that coarse-grains to the canonical state. So now, define the free energy as the difference between the actual energy and the energy the system would have if it was in the canonical state at the same J entropy. So the free energy is indexed by J. So different coarse-grainings give different energies, different free energies. The free energy is the difference between the amount of energy I've actually got and the least energy I can have, which is to say the free energy is the upper limit of how much energy I can get out by manipulating the system with transformations compatible with the coarse-graining. So that's the best we can do. We'll never get out more. If all our control processes commute with J, we'll never get more energy out than the free energy with respect to J. And instead, we'll usually get less out because generally control processes increase the J entropy. And any time I'm doing that, I'm leaving energy on the table. Because now, if I increase the J entropy, then the lowest energy I can get out is most energy I can get out is by going to the canonical distribution at this new higher value of the J entropy, and that state has more energy than the previous one. So the most I can do is get the free energy out. If I'm careless, I'll get less than the free energy out. Shows I'm doing my slides too late at night. This is the same thing said again. It's so important, we'll say it twice. That was deliberate. And so the work I can stick to, really, again, to say the same thing again, but just to drive it home, the work I can get out through any J-compatible control theory is less than or equal to the change in free energy with respect to J. Okay, let me show you some examples to show how that works. So start with equilibrium thermodynamics. So in equilibrium thermodynamics, where remember the coarse-graining map is equilibration, then the free energy is always zero. Because the free energy is the difference between the actual energy and the energy you'd have for the canonical distribution of the same J entropy. But the coarse-graining of any state in equilibrium thermodynamics just replaces it with the canonical distribution, and that has the same entropy as the canonical distribution does. So in equilibrium thermodynamics, where I just basically can't intervene on the system fast enough to stop it going to thermodynamic equilibrium, I can't get any energy out at all without adjusting the parameters. And that's what we should expect, incidentally, from phenomenological thermodynamics. If I've just got a hot box, I can't get any, and it doesn't matter how hot it is, I can't get any energy out of it without bringing in a colder box and running a heat pump between them. And if I don't have multiple systems like that I can control, if for instance, I could divide the box into two half boxes, but I can't intervene fast enough to stop the two half boxes spontaneously equilibrating, then I can't get anything out. If I've only got one system in thermodynamics, the only way I can get energy out is by manipulating these other parameters. If I've got a single box of gas, for instance, I can just let the piston out slowly, and I'll get energy out that way. The inner cycle clause does a lot of work in operational versions of thermodynamics. You can't get energy. You can't turn heat into work in a cycle. You can absolutely turn heat into work on a one-off basis. If I adjust one of the parameters and leave it adjusted, if I just let the gas expand and let it push a piston, I can certainly get some energy out. But that's the only way I can do it in full equilibrium thermodynamics. There's no free energy. In partial equilibrium thermodynamics, remember I've got a bunch of systems and the individual systems equilibrate separately. Now there's non-zero free energy. Remember our characterization of the thermodynamic canonical temperature and chemical potential in terms of the canonical distribution. Now there's non-zero free energy if my subsystems have different canonical temperature and different chemical potentials. So if I have access to the control operations of partial equilibrium thermodynamics, and if I've got two systems which are in fact at different temperatures, or different canonical potentials, now I can get some energy out. Now notice that dual requirement, we're going to come back to that. I can get energy out if A, I've got a control feature sensitive to certain features, and if I have enough information about the system to exploit those certain features. So even if I have access to partial equilibrium thermodynamics, it won't do me a bit of good if all the systems I have are at the same temperature and the same chemical potential. And conversely, if the systems are at different temperatures or different chemical potentials, but all I've got access to is equilibrium thermodynamics, that's no use to me either. The system will spontaneously equilibrate before I have a chance to grab the energy and charge my phone. And if you want to think how we get the energy out, of course, the answer is we run heat pumps or chemical pumps. We allow the two systems to reversibly approach equilibrium while siphoning off the free energy, the literally free energy, the spare energy in the process. And if I allow them to approach equilibrium irreversibly, I'll get less energy out than the free energy. I'll leave energy on the table. That's the irreversibility of the process. And that's that general point I was saying, that the free energy is the upper limit. If you do things irreversibly, you get less out than that. And notice the irreversibility, because given a control theory that's compatible with J, J entropy can increase but not decrease. The only reversible processes are the ones that leave it alone. It's irreversible if it allows the J entropy to increase, provided I only have access to J compatible operations. In Boltzmannian thermodynamics, there's free energy available if the probability distribution over those Boltzmann macrostates doesn't match the canonical distribution. So in Boltzmannian thermodynamics, if I happen to know that all the air is in one corner of the box, I can slam down a partition. And then I can slowly, reversibly expand the partition, and I can snaffle some of the energy. In the equilibrium thermodynamics, you consider I can't do that. I don't have control operations fine-grained enough to take advantage of the fact the system is momentarily away from equilibrium. I can't get my partition in quickly enough before the system is expanded. It goes back to that point from earlier, the idea that in phenomenological thermodynamics, we're assuming that I can't control the system on the timescale to which it equilibrates. In Boltzmannian thermodynamics, I can snap my partition in like that, and I can get some energy out. And the way I get it out, again, is effectively I reversibly flow to the canonical distribution. So if all the air is in the corner of the room, for instance, once I've snapped my partition in place, I very slowly expand it, and at the end of that process, the system it's not literally in the canonical distribution, it's in a state Boltzmann indistinguishable from the canonical distribution, and now I've got all the free energy out. If I'm too quick, I don't get all the free energy out. And finally, in reversible thermodynamics, if the probability distribution over microstates doesn't match the canonical distribution, in other words, if the distribution is anything other than the canonical distribution, could be in one corner of the box, but it could be something much more complicated, then there's free energy. I get the free energy by reversibly flowing to the canonical distribution. But in reversible thermodynamics, where there's no coarse-graining operation at all, and I have all the control operations, everything's reversible. If I can perform a control operation, I can perform its inverse. So in reversible thermodynamics, you never waste free energy. If you didn't get if you did a transformation that didn't get all the free energy out, all the free energy you didn't get out is still there waiting for you to get it out later. That's the sense of it being reversible. Okay, so let me draw some general themes from that set of ideas, and this goes back to the comment I made briefly earlier. There's a lot of discussion sometimes in philosophy of thermodynamics and stat mech as to this idea that physicists like, that information is a resource, that knowing more about a system lets us do things thermodynamically. And there's a lot of pushback, and you get people wanting to say, well, just if you happen to know the exact microstate of the gas, it wouldn't change its temperature, it wouldn't change what you could do thermodynamically. Well, this kind of framework gives us a sort of handle to see what's going on there. So if our control theory is forward compatible with J, everything I need to know about work extraction comes out from what the coarse-grained entropy is and what the actual energy is. That's enough to tell me the free, and the external parameters and other conserved quantities. That's enough to tell me the free energy. That means information about the state is a resource, because if I know less about the state, it's going to have a higher Gibbs entropy, but only insofar as I can manipulate the degrees of freedom to which the information pertains. In other words, only insofar as knowing more about it means it has a lower J entropy. In other words, it's only if I know things about those degrees of freedom that the coarse-graining permits me to influence that I can get something out. So in equilibrium coarse-graining, information is just useless. I don't learn anything from the microphysics of what's going on. All that matters is the equilibrium state. In partial equilibrium coarse-graining, detailed information about the subsystems is useless, but information about the subsystem energies is useful. So it doesn't help me to know the exact positions of the particles in this box, but if this box is hotter than that box, that's useful. And if I don't know which of the two boxes are hotter, that's less useful, but it's going to be useful for me to shove a thermometer in, pay a small energy cost to find out which is the hotter box, and then get the rest of the energy out. It's not going to be useful for me to gain more fine-grained information about the boxes than which is hotter, because that's not information I have the control tools to use. In Boltzmannian coarse-graining, knowing the macrostate is helpful. If in fact all the air is in the corner of the room, knowing that lets me get some energy out in Boltzmannian coarse-graining. But knowing information finer-grained, that's not useful. And in reversible thermodynamics, everything is useful. In the limit where I have access to all control operations, anything I know about the system is a resource I can use to charge my phone. Here's just a very, I'm probably started about 10 past, probably about 5 minutes. Yeah, that should be about fine. Yeah. So here's another quick example just to make the same point. This is an example that's come up in some discussions of the Gibbs paradox. Suppose I've got one box that's full of chlorine 35 and one box that's full of chlorine 37, two different isotopes of chlorine. Is it thermodynamically useful to know that one of them is 35 chlorine and 37 chlorine rather than there's the usual mixture? And the answer is yes, but only if I've got a semi-permeable membrane that lets 35 chlorine through but not 37 chlorine through. There's one control theory appropriate to people who have those membranes and a coarse graining that applies to it, and that's a coarse graining that doesn't change the isotope density in a given box. And there's another coarse graining that's appropriate for people who don't have those membranes, and that's the one that does not preserve the isotope density in the box. According to the control theory defined by the membrane coarse graining, then a state where all the 35s in one box and all the 37s in the other box has lower entropy than the state when they mix together. According to the control theory appropriate to a coarse graining when you don't have those membranes, those have the same entropy. Which is the right entropy? Well, thermodynamically speaking, that's not a good question to ask. Entropy is relative to the control operations I have available. Okay, I'm pretty much done, but let me wrap up by sort of closing the circle back to some of the ideas I started with. So I started with the idea that thermodynamics has these irreversible, has these sort of approximate fuzzy degree of controllabilities, and in some senses sort of emergent or high level, and the idea that thermodynamics is sort of precise and exact in those respects. And I want to illustrate that by going back to Maxwell's demon, to our demon that supposedly can lower entropy. And I want to distinguish two different sorts of Maxwell demon that sort of show up at these two aspects. So, a demon of the first kind is a demon that can decrease some value of the coarse-grained entropy. For instance, the Boltzmann entropy, the entropy appropriate for the Boltzmann coarse-graining. So a demon of the first kind, you're given a coarse-graining J, there's an entropy associated with J. And a demon of the first kind is a demon that can decrease the J entropy. So in fact, demons of the first kind are indexed by my control operations. They're indexed by what coarse-graining is. A demon of the second kind, I should say, what's the point of a demon of the first kind? The main use of a demon of the first kind is this. Sometimes you run into physicists or philosophers who say entropy can never decrease. If you've got a demon of the first kind, you can irritate them. Whether this is a good thing to do or not depends on how drunk you are, how obnoxious they're being, how obnoxious you're being, but it's not it's a convenient thing to be able to do sometimes. A demon of the second kind can violate the Carnot inequality. It can, and what I mean by that is it can turn heat to work in a cycle. It can take a hot box that's fully equilibrated, and it can extract energy from it and keep doing it until the box has cooled down as far as you go. It can take the ambient air and it can pull heat out of it. It can keep doing it indefinitely. It's not just it happens to have some specific information about a particular chunk of hot space. You can just keep giving a hot system indefinitely, and the demon of the second kind can keep getting work out. The main use of a demon of the second kind is to become the richest person in the world. Demons of the first kind are fairly straightforward to build. All that a demon of the first kind is a demon whose control operations are not forward compatible with the J operator that defined the J entropy. So, for instance, in my example of the chlorine, if my coarse graining does not respect chlorine framework, so if my coarse graining is appropriate to an agent who doesn't have access to semi-permeable membranes, a demon of the first kind is just a semi-permeable membrane. If I was using entropy as defined by a coarse graining that doesn't permit semi-permeable membranes, then of course a demon with access to semi-permeable membranes can decrease entropy. So in a sense, all that a demon of the first kind shows you is you'd had the wrong coarse graining. The coarse graining wasn't apt to the situation you're interested in. Demons of the second kind are impossible. Because even in completely reversible thermodynamics, the most I can do is get out the free energy. Once I've got the free energy out from the system, I can't get any more energy out after that. There's no assumption of irreversibility in that. It's true even if I have access to complete control operations. So the impossibility of demons of the second kind, the impossibility of a demon that can get more out of the system than its free energy, its fine-grained free energy, that is a constraint, a genuine constraint on thermodynamic control theory that does not rely at all on irreversibility, or any kind of coarse-graining or approximateness. Okay, so to wrap up claims, I've tried to show, in just giving this kind of way of thinking about thermodynamics, I should say, in a sense, the real point of the talk is to give this way of thinking about thermodynamics, but here are some sort of lessons to draw from it that go back to my motivation. The irreversibility in thermodynamics is coming, in part, of course, from the minus first law, in part from spontaneous equilibration. But not just from the first law, it's also coming from the time asymmetric constraints on control operations. The appropriate control theory that characterizes phenomenological thermodynamics, for instance, is a control theory which involves a very demanding coarse-graining, something like partial equilibration, and many operations are increasing in the entropy defined by that. No operations in that control theory are decreasing, and so that control theory has an irreversibility in it, which comes from those time asymmetric constraints. Where are those grounded, incidentally? I've said nothing at all about this. Nothing in anything I've said in this talk says anything about why we have this quantity that increases rather than decreases, and how that's compatible at the microphysical level with time reversal symmetry. Effectively, it's going in by fiat because I'm considering an agent who sequentially does things, and the very notion of an agent who sequentially does things is building in a certain directness of time. But if we want to ask how is it that agents are like that and we don't have time-reversed agents, that's a statistical mechanical question outside the scope of this framework. But even a fully reversible and hence fully time-symmetric thermodynamics satisfies the versions of the second law that say you can't turn heat into work in an indefinite cycle, you can't allow energy to flow from a cold system to a hot system without needing to put some work in. Those are constraints coming from the laws of thermodynamics that are constraints even on fully reversible systems. They are, if you like, inequalities that fully reversible systems always saturate, whereas irreversible systems often fail to saturate, but they cannot be violated even in fully reversible systems. And hence, whether or not we have reversibility, we still have thermodynamics. And I'll stop